The disjunction of A and B, denoted A disjunction B, says intuitively that one of A and B holds, or perhaps both hold. The sentences A and B are called the disjuncts of the disjunction. Here are some examples of disjunction. I am in Rome, or I have lost my way. 4 less than x or y less than 3. The train is at the station, or the train is moving. There are many subtleties involved in the disjunction, as we will see later. Let us at this point only note that disjunction can, in principle, be used in two different meanings. The first is the inclusive meaning, which allows both disjuncts to be true, as in the intended meaning of the sentence. You can sit next to an English speaker, or you can sit next to a logician. Well, conceivably, an English speaker can also be a logician. The other reading of disjunction is the exclusive meaning, which does not allow both disjuncts to be true, as in the intended meaning of the sentence, I can carry 2 small bags, or else I can carry 1 large bag. We favor the inclusive reading when the choice is not clear. Accordingly, when we give a mathematical definition of the meaning of disjunction, it is going to be the inclusive meaning. The implication from A to B, denoted A arrow B, says intuitively that if A, then B. Note that this says nothing about B in the case that A is false. A is called the antecedent or hypothesis of A arrow B. B is called the consequent or conclusion of A arrow B. When implication is used in mathematical or natural language, it has a meaning that there is something in A which is sufficient for the truth of B, or that A causes B. But in propositional logic we take the very simple approach to implication, that the truth of A arrow B is completely determined by the truth or falsity of A and the truth or falsity of B, with no regard to whether there is some connection between the two. The fact that this does not quite fit our everyday use of if-then is the price we pay for using the formal language of propositional logic. There are more involved formal languages which avoid this, but then one pays other prices. Let us look at some examples. If it rains, then the streets are wet. Note that this sentence says nothing about the wetness of streets when it does not rain. Maybe the streets are dry, or maybe people are hosing their gardens and the streets are wet. All it says is that if it happens to rain, then the streets are wet. Here is another example. If x less than 3, then x less than 10. This seems like a true statement about the integers. Of course, depending on x, it may be that x is less than 10, even though it is not the case that x less than 3. The sentence simply makes no claims about such x that do not satisfy x less than 3. even though we know that in such cases it is still possible that x less than 10, this sentence does not claim that. The sentence is only concerned with the cases at x less than 3. All other situations are irrelevant from the point of view of this sentence. Next sentence. If the train is moving, then the door is closed. This sentence calls for a more careful analysis. Let P0 be the atomic proposition, the train is moving, and P1 the atomic proposition, the door is closed. Then P0 arrow P1 says, if the train is moving, then the door is closed. Note that P0 arrow P1 makes no claim about situations in which the train is not moving. We can perhaps imagine that the computer inside the train is following some indicators all the time, or let's say once every 3 seconds, making sure that certain safety constraints are met, one of which is P0 arrow P1. The computer checks every 3 seconds whether the train is moving. If the train is not moving, the constraint P0 P1 gives no reason for action, and the computer moves to the next constraint. This happens every 3 seconds, until the train starts moving. Then the computer detects a movement and rushes to make sure the door, or rather the doors, are closed. The computer simply makes sure that every 3 seconds the implication P0 arrow P1 is true. For the computer, the meaning of P0 arrow P1 is, if P0 is false, move on, but if P0 is true, then make sure also P1 is true. This is the genuine meaning of implication in propositional logic. The equivalence of A and B, denoted A double arrow B, says intuitively that A holds if and only if B holds. Here are some examples of its uses. The lamp is lit if and only if the switch is on. X less than 10 if and only if x plus 5 less than 15. The door is locked if and only if the train is moving. In each case, the intuitive meaning of A double arrow B is that either both A and B are true or else they are both false. Equivalence is a relatively unproblematic logical operation, nothing like disjunction and implication. The main connective is a useful technical notion related to formulas. Locating the main connective is quite easy. The main connective of not A is negation, A and B is conjunction, A or B is disjunction, A arrows B is implication, A double arrow B is equivalence. For example, the main connective of left parenthesis A or not B right parenthesis implies left parenthesis C or D right parenthesis is implication. The logical analysis of a formula usually starts by identifying its main connective. Therefore, the first thing a logician does upon seeing a formula is to locate its main connective, and depending on this connective, the logician decides on further action. Our rules concerning the use of parentheses guarantee that every formula has a unique main connective. That is, it does not happen that one tries to find the main connective and once it is conjunction, but another time with the same formula it is a disjunction. Another useful technical notion related to formulas is that of a subformula. Intuitively, the subformulas of a given formula are the smaller formulas that the given formula is built from. We accept the formula itself as its own subformula. The subformulas of negation A are negation A and the subformulas of A. The subformulas of A conjunction B are A conjunction B and the subformulas of A and B. The subformulas of A disjunction B are A disjunction B itself and the subformulas of A and B. The subformulas of A arrow B are A arrow B itself and the subformulas of A and of B. The subformulas of A double arrow B are A double arrow B and the subformulas of A and B. For example, the subformulas of left parenthesis B0 or not B1 right parenthesis arrow, left parenthesis B2 and B1 right parenthesis are left parenthesis B0 or not P1 right parenthesis arrow left parenthesis P2 and P1 right parenthesis P0 or not P1 P2 and P1 P0 not P1 P2 and P1. Special among subformulas are immediate subformulas. They are just as easy to find as a main connective discussed above. The only immediate subformula of negation A is A. The immediate subformulas of A conjunction B are A and B. Of A disjunction B, the immediate subformulas are A and B. The immediate subformulas of A arrow B are A and B. The immediate subformulas of A double arrow B are A and B. For example, the immediate subformulas of left parenthesis P0 or not P1 right parenthesis arrow left parenthesis P2 and P1 right parenthesis are left parenthesis P0 or not P1 right parenthesis and left parenthesis P2 and P1 right parenthesis. Thus, a propositional formula is always formed by connecting the immediate subformulas by the main connective. This sounds so easy that one may ask, is this knowledge of any use? Yes, it is. A whole lot of use. All fundamental methods of logic are based on analyzing formulas in terms of their immediate subformulas. We learn several of them: evaluating truth, natural deduction, semantic tree. So, it is worth being comfortable with the concepts of main connective and immediate subformula. This ends the first lecture on propositional logic. In the next lecture, we will discuss truth tables.